All right, let's work through the bell work. What's our instinct on this first one? What did we do? On this one. What can we do? What did we do? Because we're supposed to work on it while I'm doing attendance, right? So we totally did. Because this is review. This is old school. This is exponent laws. What can we do? There's a couple of different ways you can go. It's going to take us a very long time today if you guys aren't willing to voice things. What can we do? Yeah, we can combine our numerator. So we can make this to be x to the 4 plus 2. Since we're multiplying the bases, we add our exponents, which gives us 4 to the 6th, or I'm sorry, x to the 6th over x to the 3rd. What else can we do? Six minus 3. So this is going to simplify down to be x to the 3rd. So when we multiply the bases, we add the exponents, and when we're dividing the bases, we subtract the exponents. You could also do this as a negative exponent and land with that up here and add. Either way, that's totally fine. This right-hand one is a very similar vibe, except now we only have fractions. So with my x's, what exponent are we going to have? If we just look at the x terms. Two. And is it going to be in the numerator or in the denominator? The denominator. So we have x squared in the bottom. You could also think of this as 1, 2, 3, 4, 5 x's on the top, and 1, 2, 3, 4, 5, 6, 7 x's on the bottom. And you can see here how a lot of them cancel out except for 2 on the bottom. This is our x squared that we had underneath. So you can think of it as subtraction. You can think of things canceling out. However works for your brain. How about my y's? It's going to be y squared, and is it going to be on the top or on the bottom? Y squared on the top. How about the z's? Z to the first, numerator or denominator? Denominator. And this is our simplified form. So these old school exponent laws are going to be relevant to what we're doing. Because what we're going to be out of graphing today. Thank goodness, right? So we're out of graphing today, but we're going to go back into simplifying stuff to start getting ready towards solving things, which is what we're going to do next week. So this is using what we just did in exponents, talking about when we're multiplying pieces together and when we're dividing pieces together, but they have square roots. So these are the two properties we're going to use today. And Monday we'll do adding and subtracting stuff. Tuesday, Wednesday we'll do solving stuff. Thursday's review. Friday's the quiz. That's the general plan for next week. So what we're going to do when we have things that are in square roots, let me change this page so it stays up. Our product property is where I'm multiplying two things in square roots. And what we can do is we can just take both of the things that are under the radical and multiply them together. Then we need to simplify. And this is true with all radicals, not just square roots. Like that works with cube roots too. And when we have two radicals divided with each other, we can take and divide x and y. Or you can write it as the square root of x over the square root of y. Those all mean the same thing. And again, we need to simplify these as much as possible. Which we've worked with simplifying before, and we in fact started working with this, but we're going to focus on these a bunch today. So we kind of touched on these before when we were starting to simplify our radicals. We're going to work with those again. Because what we're going to do is we're going to look at what our rules are for when it's fully simplified, when we get to stop. This is what we need to have in order to be able to stop. We need to, the radical expression in the simplest form is that we have our index simplified. The radicand doesn't have any more perfect squares in it. And that we've simplified our fractions fully. So it either needs to be split apart or expressed in a different way. So we're going to practice some simplifying stuff. And here's where we're going to start. We're going to start with the square root of 75, x to the 12th, y to the 7th. We've done something like this before. But it's been a couple of days, so we need to remember. What is our index on this one? 2. We just don't have it written here, but the index is 2. So that means we're going to be looking for perfect squares on things. So we're going to use that product property and split this into separate pieces just like we did last week when we make it easier for us to work with it. This uses that product property. Just because we can take things and multiply them together doesn't mean we can't also pull them apart. What can we do with the square root of 75? Yeah. We can split this apart again and make it 25
Pardon this interruption.
times
Reader
3.
testing continues this morning with reading group F, testing in room X214. Teachers, please check your email for today's student testing list. This is the only group testing today. Thank you.
Ooh, small amount of testing today. We like that. We are splitting it apart into these two different groups because I can split this again and do square root of 25 and the square root of 3. Because what is the square root of 25? 5. Because 25 times 3 gives us 75. And I'm splitting it apart again because 25, I know. Square root of 3 is a gross decimal, so we're just going to leave it in the radical. How about the square root of x squared? What are we going to get? X to the 6th. Say, I think you were thinking it right. It just didn't. We just didn't say it right. Yeah, because what we're going to do is we take our power and divide it by our index. This is what we did. Like, I don't remember if it was earlier this week or last week, where we take our power and divide it by the index. So we're going to get x to the 6th. I'll put it way down here. I'll find this 5. So x to the 6th. And it's not in a square root anymore. But it's our power divided by our index, which works perfectly well when it comes out as a whole number. When we have something that would leave us with a fraction, what do we need to do? What we need to do with this y. Yeah, I can rewrite y to the 7th as something that would divide by 2. So I can make that y to the 6th and y. Exactly right. It means the same thing. Y to the 6th times y is y to the 7th. But we like it like this because square root of y to the 6th we can do with our power over index. And the square root of y is a thing. So the square root of y to the 6th is what? Y to the 3rd. And then we're left with our square root of y. These are all the simplified pieces. We just need to reorder this because that looks like chaos. So we put everything outside the radical together. My 5, x to the 6th, y to the 3rd, and my things that are inside the radical together, 3y. I don't have any more perfect squares inside my radical. My radical has been fully simplified. I don't have any weird fractions under the radical. This is my simplified answer. Okay, so we've worked some like this before, but we're going to be doing a lot of work using simplifying next week, so it's really important that we remember how to simplify. So that's what we're focusing on today. We're remembering our simplifying stuff. So they will get a little bit more complicated, but you know it's a thing. There we go. I was glad to put it all up. So we're going to do the same thing over here, but this time we're dealing with a cube root. So once again, I'm going to take and we're going to split this apart into products of all of my pieces. So we're going to have the cube root of negative 27. We have the cube root of x to the 6th. And my cube root of y to the 14th. What is the cube root of negative 27? You can type it into the calculator, or we can remember that 3 cubed is 27. So negative 3 cubed is negative 27. How about the cube root of x to the 6th? X squared. Gorgeous. Hard ones are y's on this one, because we need our 14 to be divisible by 3. Because we took our power and we divide it by our index. So we're going to take our x to the 6 divided by 3. And 6 divided by 3 gives us 2. So that's how we simplify these powers. We're going to take our power and divide it by our index. But if we try and do that with the y's, we wind up with a fraction, and we don't want to have that. So what I'm going to do is I'm going to split my y apart into 2 chunks. One chunk that is divisible by 3 and one that's not. So I can rewrite y to the 14th as y to the 12th times y squared.
Why can't you do the same thing you did last?
Because 14 divided by 3 won't simplify to a number. It's just a fraction. So we need it to be divisible. So I can take it and split it apart into pieces, and then we will do exactly the same thing. We're going to do y to the 12 divided by 3. And 12 divided by 3 is 4. But if I left that as 14 over 3, we'd get a weird decimal. And we're not doing decimals. So then we're going to have our leftover cube root of y squared inside there. When we are done simplifying, all of our powers that are under the radical should be smaller than the index. That's how we can tell we've got all the pieces out of there. So our simplified answer here, we're going to take all of our pieces and write them down next to each other. Negative 3 x squared y to the 4th, and then the cube root of y squared. As long as all of our exponents that are left under the radical are smaller than our index, we've gotten there. The 12, I took 14 and I broke it up into a piece that was divisible by 3, so I used this as my tool. I need the biggest piece that I could split 14 into a sum. So 12 plus 2 still gives me 14. 13 and 1 doesn't help me. 11 and 3 doesn't help me. I need something divisible by 3. That's the biggest one we've got. So we need the biggest sum that's divisible by 3. We're going to try this a few more times for surezies. Because the simplifying is a little weird, and it's been several days since we've done it. Okay. Ready? All right, so our next run, we've got a cube root, and this one's a fraction this time. So we're going to use that quotient rule we wrote at the beginning, where if I have one fraction, what we can do is we can split it apart into two pieces. I can do the cube root of the numerator, 24a to the 6th. And I can do the cube root of my denominator, 125. Then what we're going to do is I'm going to look at each of those pieces individually. My cube root of 24a to the 6th. And we're going to do that just like we did the pieces on the last page, where I split it up into a product. The cube root of 24 and the cube root of a to the 6th. My first question is 24 a perfect cube? No. Boo. Does it have a perfect cube as a factor? Which one? 8. Yeah. I can rewrite 24 as 8 times 3, right? And we can do the cube root of 8. Cube root of 8 and the cube root of 3. What is the cube root of 8? 2. So this is 2 cube root of 3. How about for this a cube root of a to the 6th? Yeah, this one we can just bring on down. That one's just a squared. We're going to take our power divided by our index. So it's a to the 6 over 3. And that's how we get that a squared. So our numerator in our fraction up here becomes 2a squared cube root of 3. Because we put everything outside the root in front and inside the root at the end. Then we need to look at our denominator and simplify that. We need the cube root of 125. What's the cube root of 125? 5. It just straight up is 5. So our denominator is 5. Okay, so there's a lot of different pieces in these that we're going to be working with. So the next one we're going to look at is a little trickier. Because it's a fourth root. And we haven't worked with fourth roots of numbers all that much. So we're going to start with splitting this apart into our two different fractions first, where we have our fourth root of 80 y to the 14, and my fourth root of 256 z to the 4th. I'm going to run out of space, but that's okay. So we're going to look at each piece individually, and I'm going to give myself a little barrier up here so that I can use any of the space that I need to. So I'm going to start with my numerator. We're looking at 4th root of 80 y to the 14th, which we can then split apart. Oh, I did an error there. To be our 4th root of 80 and our 4th root of y to the 14th. And what we need to look for is we need to see if there's any perfect fourths inside 80. It's not a perfect, 20 is not a perfect fourth. So that's one weird thing because we haven't worked with fourths at all. So let's make a list real quick on the board. Grab a curve. So when we're dealing with weird roots, make yourself a list of values for us to spot easily. So 1 to the 4th is 1. That doesn't help us much. What's 2 to the 4th? 16. What's 3 to the 4th? And like y'all can use calculators too. It's 81. Four to the 4th, 256. So these get real big, real fast. Are any of those factors of 80? We know it's not 3 because 81 is in fact bigger. Does 16 go into 80? Utilizing tools at our disposal? Yeah. We can rewrite 80 as 16 times 5. And we can then split those apart to be the 4th root of 16 and the 4th root of 5. We just saw on the screen the 4th root of 16 is 2. And then we have our 4th root of 5 that's just going to hang out. How about our y to the 14th? What do we need to do there? What are we going to split the y up into? 12 and 2. Because then we can do our y to the 12 over 4. We can divide our power by our index. And I'm actually going to write the other one like that as well so we can see what we mean by simplifying. 2 over 4. 12 over 4, when we simplify that, what happens? We get y to the I'm going to change the view. It's going to pop in rows of closer. Y to the 3rd. What can I do with this piece here? Y to the 2/4, can that simplify? To the 1/2. So we can actually simplify our root. I like it, but we can do it. So when we are looking at this and we're trying to rewrite our numerator, we can have 2 y to the 3rd square root of y, 4th root of 5. And that is so gross, but that's what it is. That's what they were trying to get you to see, but why they didn't give us a perfect cube or a perfect fourth there, I don't know. How about our denominator? What's going to happen with that? What is the 4th root of 256? 4. What is the 4th root of z to the 4th? Just z. So we've got everything as simplified as we can possibly get. I can't do anything else. That's as far as we're going to go. And that is really hard to see. That gray is very light. Oh. I'm just going to write this a little bit darker. No, with a pen. There we go. Yes, dear. Yeah, let me write your pass. Okay, we're only going to do one more page of these. And they're not awful. The last page is way harder. 4th root of 4x to the 5th, y to the 20. Can we do the 4th root of 4? No. It's not my list of fourths. So let's put that to a side for now. How about x to the 5th? What are we going to get? What are we going to get when we try and take the 4th root of x to the 5th? Let's see if we can do it with more by yourselves. What do you think?
X to the 4th times x.
Yeah. We can split it up to be the x to the 4th and x. So when we simplify it, what are we going to get? X times the 4th root of x. So this guy's going to stay inside. So he's still going to stay in the house. How about 4th root of y to the 20th? What are we going to get there? Y to the 5th. 20 divided by 4. So we're going to have as our answer our x, y to the 5th, 4th root of 4x. And I encourage you to try the last one, but honestly, we have 4 minutes till announcements, so I'm not going to take all of our time to do that because I'm going to pass out the next homework. We've only talked about half of it, so just so that we're aware, we'll talk about half of it because we're going to do adding and subtracting stuff on Monday. So we're going to take radical statements and add and subtract them. So you can do the simplifying stuff, and we can maybe do some of the multiplying stuff. Okay, so this is mostly about remembering how to do our All right. Oh, my iPad is dying. It's low on juice.